All right, chemistry, we're going to continue in this lesson with the study of gas laws. So the relationships of Boyle's, Gay-Lussac's, and Charles' law are as follows. Boyle's law says that there's a relationship between pressure and volume. The pressure times the volume before equals the pressure times the volume after a change. Gay-Lussac's law relates temperature and pressure, and Charles' law relates temperature and volume. You do not need to memorize these by name, but they're just simply relationships. They can all be combined into the combined gas law, which is the pressure times the volume divided by the temperature before a change equals the pressure times the volume divided by the temperature after a change. There's one major formula that relates the four variables of gases. It's called the ideal gas law, and it says that the pressure times the volume equals the number of moles times R times T. R is the gas constant. So PV, T, and N have been defined previously: pressure, temperature, volume, and number of moles. R is called the ideal gas constant, and it's this number down here, 0.0821 liter atmospheres over moles Kelvin. So the purpose of this constant is that it cancels the units of measurement so that only the units of the final answer appear. So the ideal gas law is a central formula for the study of gases. An ideal gas is a gas in which the gas particles don't interfere with each other. So if you think of a single atom of gas in outer space where there's no other molecules, that would be a perfectly ideal gas. So the ideal gas law, PV equals nRT. So P is pressure in atmospheres. V is volume in liters. N is number of moles. T is the temperature in Kelvin. And R is the ideal gas constant. So think of the gas constant as several conversion factors wrapped into one number. R causes all the units to cancel except the one needed in the final answer. The other thing it tells you is what units you need to be working in. For example, we learned that there are several different measures of pressure, including torr, pascals, and so on, but you have to be working in atmospheres to use this gas constant. Liters, okay? If you're given milliliters, you have to convert to liters. Number of moles is simply a number. Temperature has to be in Kelvin. So if you're given the temperature in centigrade, you have to convert to Kelvin before you put the numbers into this formula. So there's the ideal gas law. So think of the gas constant as 6 conversion factors wrapped into one number. So example, if you solve the gas law for temperature, you get PV over nR. The gas constant R will cause all units of measure to cancel except the temperature in Kelvin, and that's the unit for temperature. Okay, so what happens to pressure when volume is increased? Okay, so if you look at it mathematically, look at the equation. If V goes up, then T has to go down mathematically because they both have to equal, when you multiply them, nRT. So the variables in black are staying constant. V is going up, T is going down. So if nRT remain constant, then as V increases, T decreases because the particle hits the side fewer times. The relationship between pressure and volume is called Boyle's law. So there you see, if we expand the volume of the container, and we think of pressure as the number of times that particle hits the container. So by expanding the volume, assuming it maintains the same speed, which it does because the temperature stays the same, then that means that it's going to hit the sides fewer times, and that's a lower pressure. Okay, what happens to pressure when temperature is increased? So now you see mathematically that pressure and temperature are on opposite sides of the equation. So if N, R, and V remain constant, then as temperature increases, pressure increases because the particle hits the side more times. It's moving faster. The relationship between pressure and temperature is called Gay-Lussac's law. What happens to volume when temperature is increased? So we're going to assume that pressure stays the same, the number of moles stays the same. So if N, R, and T remain constant, as temperature increases, volume increases. For the particle to hit the sides the same number of times, that's what constant pressure means, while moving faster, higher temperature, that means the volume must get bigger. And this is called Charles' law. Okay? So if you follow the helium on the left, it's hitting the sides about 4 times every 2 seconds. The one on the right is also hitting the sides 4 times every 2 seconds, but it's going a lot faster. So if it's going to maintain the same pressure 4 times every 2 seconds and go faster, then that means the volume must expand so that it has to travel a farther distance. What happens to pressure when the number of moles is increased, assuming all other variables are the same? So if you increase the number of moles, you're going to have more particles inside the container. So if T, R, and V remain constant, then as the number of moles increases, pressure increases because there are more particles hitting the sides. The relationship between pressure and number of moles is called Avogadro's law. Okay, we did this exercise earlier, unit cancellation. So as we move further into the course, unit of measure cancellation will become more complicated. Use the principles of fraction division to cancel units. Okay, so if 2 levels of the fraction have a word in common, then the units on those levels can be canceled. Okay, so we are going to say that we have a fraction on top called the numerator fraction and a fraction on the bottom called the denominator fraction. Now the top of the numerator fraction we'll call numerator top, and the bottom of the numerator fraction we'll call numerator bottom. The top of the denominator fraction is denominator top, and the bottom of the denominator fraction is denominator bottom. So if a variable you're thinking of canceling has one of those words in common, then that means it can be canceled. So let's look at an example. So there you got a crazy quilt of different units. So this is just as an exercise. You would never see this in a real problem. So let's go ahead and let's look at K. So you notice that K is in numerator top and in numerator bottom. That means they both have the word numerator in common, so they can cancel. If you look at atmosphere, atmosphere is in numerator top and denominator top. Since they both have the word top in common, they can cancel. Okay, there's L. There's L in numerator top and in denominator top. They both have the word top in common, so they can cancel. Okay, there's grams. Now you see grams down at the bottom. There's grams in denominator top and in denominator bottom. They both have the word denominator in common, so they can cancel. And there we have mole in numerator bottom and denominator bottom. They both have the word bottom in common, so they can cancel. The only ones we're left with is grams in numerator bottom and liters in denominator bottom. So we come over here and we come over there, and what you do is you have 1 over grams over 1 over liters, and of course fraction math says you flip the bottom and multiply, so what you're going to end up with is liters over grams. Standard temperature and pressure, you need to know this well, have it memorized, is simply the temperature at 0 degrees, which is 273 Kelvin, and 1 atmosphere of pressure. So that's basically the freezing point of water and the pressure that you feel in this classroom right now. Now, that may seem pretty cold, 0 degrees centigrade, this freezing point of water, but for diatomic molecule gases like hydrogen, H2, O2, N2, that's very, very warm because they freeze much, much lower than 0 degrees centigrade. So using STT and the ideal gas law, we can determine the relationship between the number of moles and the volume of a gas. We can determine 1 mole of gas is equal to 22.4 liters. So let's go ahead and plug in the numbers here. So there's PV equals nRT, and we're going to solve it for volume. So you have volume equals nRT over T. So we're saying, assuming that we have 1 mole of gas, there's the ideal gas law, and we're going to say the temperature is 0 degrees centigrade or 273 Kelvin, and down in the bottom we have the pressure of 1 atmosphere. So let's cancel our units. So we've got Kelvin and Kelvin cancel, that's numerator top, numerator bottom. Okay, we have moles and moles cancel, that's numerator top, numerator bottom. And we have atmospheres and atmospheres cancel, that's numerator top, denominator top. And the only unit then we are left with is liters. And if you do the math on that, you see that the answer is 22.4 liters. So 1 mole of any gas is equal to 22.4 liters. It doesn't matter what the gas is. Hydrogen, H2, O2, anything. It's going to equal 22.4 liters. That's a very important relationship to remember. And that's only at standard temperature pressure. Okay, so let's do a little bit of stoichiometry, and we're going to add another variable here. We're going back to our flow chart for moles and grams, but we're also going to add liters up on the top. Okay, so we can also measure things in liters. So here's a question. How many grams of H2O will be produced from the combustion of 12.4 liters of CH4 at standard temperature pressure? Because that 1 mole equals 22.4 liters is only true at standard temperature pressure. So we're going to go ahead and we're going to put 12.4 liters above CH4. All right, now we're going to combust that. So we need to go through the relationship 1 mole equals 22.4 liters, and that's going to take us down into moles of CH4. So now we're in moles of CH4. We need to move across to moles of H2O. And then from moles of H2O, we move down to get into grams of H2O, and that's our final answer, okay? So we set up the equation just like we always have. Over on the right, we're going to have grams of H2O, and over on the left, you see up there is 12.4 liters of CH4. So the first equivalency is 1 mole equals 22.4 liters. That is for any gas. So there's the two conversion factors, and the one we're going to choose is this one. So you want liters on the bottom, so that'll cancel like that, okay? And now you're sitting in the box with moles of CH4, and while you're not going to do this calculation directly, it's 0.554 moles of CH4. Now we move across from moles of CH4 to moles of H2O, and you can see that there's 2 moles of H2O equals 1 mole of CH4. Okay, there's the two conversion factors up there, so which one do you choose? You need moles of CH4 on the bottom, so that'll cancel, and now we're sitting in the box with moles of H2O, and if you did the calculation, which you do not do, it's 1.1 moles of H2O. Now we need to get out from moles of H2O to grams of H2O, so there we see the molar mass conversion there. 1 mole H2O equals 18.02 grams. And which one do you want on the bottom? You want moles of H2O there. So that cancels moles of H2O, and the last man standing is grams of H2O. And so now you simply go ahead and compute the numbers, and you end up with 20 grams of H2O. So done just like we did molar mass, except you have an added variable of liters up there on the top. All right. Okay, so that concludes our second lesson on gas laws, and includes gas stoichiometry.